All right, chapter 4 is very brief. 4 and 5 are both brief. That's why we joined them together in our last unit. 3 sections, and it's all going to be about divisibility. Okay, so it's all about how things divide. That's what chapter 4 is all about. Section 4.1 actually has the title divisibility, and the first thing we need to talk about is what we actually mean when we say divides, like from a definition standpoint. All right, so if A and B are whole numbers, then we say that D divides A. It is written as a vertical bar. D divides A. We read it from left to right. If and only if there is a unique whole number Q such that A is equal to DQ. If D divides A, then D is a factor or divisor of A, and A is a multiple of D. So fill in those blanks, and I'm going to give you an example and use that same verbal description with some numbers. Okay, so the example I'm going to use is, we'll do that one, not sure. That's 4 divides 20. Okay, so 4 divides 20, right? If I have 20 cupcakes and I have 4 people, I can divide that evenly, correct? Everybody goes home with the same number of cupcakes. So 4 divides 20, but the reason it divides 20 is because there is a number, 20 is what I wanted to write there. Oh, good grief. There is a number that I can multiply the 4 by, namely 5, right? This is my number, so that it actually will equal the number 20. We call 20 a multiple of 4, and we would call 4 a factor of 20. So factors are the things that divide. Multiples are the things that we get when we multiply. It's nice how that works, right? The description matches our other things that we've learned. Here's the deal. These numbers occur in pairs. So if we say that 4 will divide 20, then 5 will as well, right? Okay, that's what our next theorem says. Our next theorem says that if we have a whole number A and D divides A, N is a whole number. Oh, I'm sorry. I was taken back. I'm already on there's another theorem I'm thinking of already. I'll take it back what I just said before. It's a true statement. We're just not there yet. Okay. If you have it D divides A and N is a whole number, then D will divide NA. So we'll continue with my example from before. We said that 4 divides 20, which it does. It also means that 4 is going to divide 20 times any other number, say 3, right? And 4 will divide 20 times 7. And 4 will divide 20 times 12. It'll divide 20 times anything, and that's what this theorem says. So in other words, if I know that 4 divides 20, and I can break a number down so that it has a 20 in it, then I know 4 is going to divide the product as well. Okay, that's what this theorem says. Okay, so the next set of theorems, there's 5 of them. There's 5 features of the next theorem. They all go hand in hand. So they talk about what happens when we have division and addition and or subtraction, okay? So it works like this. Here's our first one. In all cases, D is going to divide or not divide A. The first one, D divides A. So D divides A, and D divides B. Then D is going to divide A plus B. And I will go back in a moment and kind of write in a different color underneath it an example so you can see it happen and go like, oh yeah, that makes sense. But I want to get them all written down first. Okay? It's going to work for subtraction as well. If D divides A, in a minute, the subtraction one. The next one's different. If D divides A and D does not divide B. Okay, so one divides, one doesn't. If that happens, then D is not going to divide A plus B. If it divides one and not the other, it's not going to divide the sum. Okay, the next 3 are all about subtraction. So if D divides A and D divides B, and we need to have some ordering of the A and the B, and it doesn't really matter what it is because we're ordering them because we're working with whole numbers. If we were working with integers, which comes into play in chapter 5, we don't need this fact. But for right now, when we're working with whole numbers, we need it. So A is greater than or equal to B. Then D will divide A minus B. And the reason that we need this fact is because I want to be able to say A minus B is a whole number. That's what I was referring to. And A minus B will be a whole number if A is bigger than B. Okay, whole number is 0. There's one more that looks a lot like this one. D divides A. All right, and D does not divide B. Okay, so we have that secondary feature that looks a little different. And still A is greater than B, greater than or equal to B. Then much like sort of property number 2 up there, D is not going to divide A minus B. And the last one almost looks like I just took this fourth one and sort of shook it up a little bit. We're going to say D does not divide A now, but D does divide B. The rest of it stays the same. A is greater than or B equal to B. And it will also be true then that D does not divide A minus B. So there's 3 for subtraction. There's only 2 for addition. And you might be thinking, well, why do I need an extra one for subtraction than I do for addition? And the reason is because addition is commutative. So in that second one up there, I could switch the B and the A around, but I can't do that down here in subtraction. So because I can't switch it around, I need to describe what happens when the first one is not divided and the second one is. I don't need to do that up there because I just flip things around anyway and I can shift which one's first and second. Okay, so let me do a real quick example on each one of these. This is not proof by example. I'm not proving anything. But I do want to sort of bolster your thinking that this makes sense. Okay, this is a justifiable sort of argument. So we're going to do something really easy. We're just going to do evens versus odds because that's a really easy one to just sort of see that it works. So we're going to say that 2 divides 4. That's great. Tell me another number that 2 divides. 8. Okay, 2 divides 4 and 2 divides 8. Is 2 going to divide 4 plus 8? Yes. Because when I add the 4 and the 8 together, I get another even number, right? Even number plus an even number is an even number, so it's going to divide by the same even number, right? What about if I do that same 2 divides 4? I'm going to use 2 divides 4 on all of them that say division parts here. And now I need a number that D will not divide. What's something that doesn't divide? 5. That'll work. D does not divide 5. Agree? I didn't mean D. I meant 2 here. I'm sorry. 2 is what I meant to write. 2 does not divide 5. So 2 divides 4. 2 does not divide 5. So what can you tell me about 4 plus 5? Well, it doesn't divide it, right? It's an odd number. So when I add an even number and an odd number together, I get an odd. And so this isn't going to work. Okay, we're going to do the same thing down here. We're going to do a subtraction. I need to make sure that the value I'm putting first is actually bigger. So let's do this one as 2 divides 10. And then I'll do 2 divides 8. I could do it to some other numbers, but those will work just fine. So in fact, the 10 is bigger than 8, which was my goal. So then will 2 divide 10 minus 8? Yes, right? 10 minus 8, again, subtraction gives me an even number. So even minus even is even. 2 will still divide that even number. So we're going to come down here. I'm going to keep my 2 divides 10 because I can. And then we'll pick something that 2 does not divide. Well, we did 5 before. 5 is as good as anything right now. 2 does not divide 5. And again, 10 is bigger than my 5. So that works. So we can actually talk about what happens now when I do 10 minus 5. And 10 minus 5 would be, again, 5. And another odd number, right? So 2 is not going to divide that. And the same thing is going to happen down here when we flip them around. I still need to have a bigger number first. So let's actually pick a number that's bigger than 10. Let's just do bigger than 10. That does not divide by 2. 15 will be great. 2 does not divide 15, right? Right. But 2 does divide 10. You could use another number here if 2 divides it if you wish. I needed to make sure that my 15 was bigger than my 10, which we did. Then notice when I do 2 and I do 15, in this case minus 10, 15 minus 10, right? Odd minus even is still going to give me an odd, and it's not going to work. Okay, everybody good? All right. So again, there's nothing that's proofy about that, but at least it develops our sense of the intuition that yes, it makes sense. Evens and evens add together to be evens, evens and evens subtract to be evens. And there's nothing special about it being even, right? I chose the number 2 because it was real quick for us to come up with numbers and to justify it real quickly in our mind. But we could have chosen any number at the beginning. I could have chosen a 37, right? I could have chosen a 12. They would all work the same way. It would still have all those same properties. Okay, the next part I think is the most interesting part for this section, the divisibility rules. Some of these you know, and some of them you do not know. Okay, so this is divisibility test for 2. The divisibility test for 2 says the following. A number is divisible by 2 if and only if the unit's digit is even. Now, I understand that the unit digit being even means the number itself is even. I get that. But the point of all of these properties is to isolate something that's really easy to see, and it usually involves looking at the last digit or the last 2 digits or something like that, okay? So all we have to do to decide if a number is even is look at the units digit, right, the ones place. And if the ones place is even, it's going to be even. Now, I had some issues in my other class with some evens and odd stuff, so I want to clarify what I mean by even. In particular, 0 counts. 0 is an even number. So this is 0, 2, 4, 6, and 8. Okay, 0 counts. Sometimes people think 0 shouldn't count somewhere. It does. It counts. 5s. Well, the property for 5 is almost identical, at least in its sort of processing, to the property for 2. I look at the units digit. And if the units digit is a 0 or a 5, it's going to be divisible by 5. Okay, so if it's any other number besides 0 or 5, it will not divide by 5. And then the third one in this category here is 10s. A number is divisible by 10, in truth, when it's divisible by 2 and 5. And 2 and 5 overlap when they're divisible by 0. Not divisible, excuse me, but have the end in 0. So if it ends in 0, it's divisible by 10. So these 3 are grouped together because they all feel very much the same. Does that make sense? In every case that's on this screen, we just look at the last digit. Now, you can't do this for other numbers. You can't say, hey, a number is divisible by 3 if I look at the last digit and do x, y, z. It's not going to have that property. I can't do it for 4s. I can't do it for 7s. I can't do it for any other numbers but these 3. 2s, 5s, and 10s. That's it. Okay? All right. Yes, RJ.
Sorry, that's to say for theorem 4.4, was it 5 cannot divide like just 0? Not if it ends in 0, but if it's just 0,
Yep.
it cannot divide that.
Yeah, well, no, 5 divides 0. So does 2. Anything divides 0, actually. If I have 0 cupcakes, I don't know why cupcakes is I know why cupcakes is on my mind. My daughter made a lot of cupcakes this weekend. If I make 0 cupcakes and I want to divide them evenly among 5 people, no problem. Everybody just gets 0 cupcakes. So 0 divides by everything. What I think you might be thinking of is what divides by 0. So nothing divides by 0. We can't divide by 0, but 0 is divisible by everything. Okay, so 0 will divide by 2, 0 will divide by 5, 0 will divide by 10. And so will anything that ends in the zeros. It will be divisible by those values. Okay, the next 2 that get grouped together are 4s and 8s. You could kind of group 2 in here as well, because it's kind of a building upon thing. So in order to do things with 2s, we looked at the last digit. When we want to do divisibility for 4, we actually look at the last 2 digits. Okay, so you look at the last 2 digits of a number, and if the last 2 digits, all by themselves, not individually, but as a 2-digit number, are divisible by 4, then the whole thing is divisible by 4. For example, let's say that our number ended in 24. Okay, it's got a bunch of numbers in front, doesn't even matter what they are, but the last 2 digits say 2 and then 4. 24. Is 24 divisible by 4? Yes, it is. And since 24 is divisible by 4, that long number, whatever it was in front of the 24 and the 24, all that together is also going to be divisible by 4. Okay? Now that's not perfect, but it's not bad. you know about half of the 2-digit numbers and whether or not they divide by 4, because your multiplication tables by 4s, which a child would have learned before they got here, go up to about 40, and it's not hard, or 48, depending on if you've gone up to multiplication by 12s, which a lot of curriculums do. That's half, right? If I can get all the way up to 50-ish, and I know if it's divisible by 4 or not, that gives me half of the values just by memorization alone. So you might be looking at this and saying, okay, but let's say that the number said 76. How do I know if 76 is divisible by 4? Well, you know, your child might actually have to sit down and long multiply and divide out and see if the 4 will divide into it. But you know what? That's better than trying to see if it divides into a 5-digit number, isn't it? That's better. If you have a 5-digit number and you're trying to divide by 4, that's a lot more work than a 2-digit number to decide if it divides by 4. So while it might not be the perfect theorem that we wish it were, it's not bad. We can work with it. 8 loses some of that ability because it looks at 3-digit numbers. Still better, right? I'd still like to divide a 3-digit number better than I'd like to divide a 5-digit number, but it becomes more difficult. So the divisibility test for 8 says if the last 3 digits as a 3-digit number are divisible by 8, then the whole thing is divisible by 8. Okay, we have to look at all 3 of the last digits and decide if those 3 digits as a 3-digit number works. And if it does, then that's great. And if it doesn't, then we know that the answer is no. Okay, so can you see how this builds upon 2s? If we did it for 2, we look at the 1 digit, the 1's digit. If you look at the number 4, we look at the 2-digit number at the end. And if you look at the number 8, you look at the 3-digit number at the end. And the reason that's happening is because 4 is 2 squared and 8 is 2 cubed. That's why you're getting those last 3 digits for the 8, is because it's 2 to the power of 3. That's why we need all 3 of them. Okay, so these 2 get grouped together. These 2 get grouped together, and you may have learned number 3, and you might not have learned number 9. I remember learning this very specifically. I don't know why it came up, but it was in a calculus class. And I remember being like, oh my goodness, nobody's ever told me that? You've got to be kidding me. These are very, very easy ones to use, and they're identical to one another. A whole number is divisible by 3 if and only if the sum of the digits is divisible by 3. And it's divisible by 9 if the sum of the digits is divisible by 9. Okay, so here's how this works. You take a long number, whatever it is. It's got 5 digits, it's got 7 digits, it doesn't matter. And you just add all those individual numbers together. And if when you add them together, what you get is divisible by 3 or by 9, then the original number was as well. We're going to practice on all these, I promise. But it's a pretty quick and easy one because we can usually add quicker, single digits especially, than we can do division. The last one, the last two, they're not really grouped together. They're just on the same slide. Okay, so the one for 11 is the most complicated to write down. I will show you how it works specifically. I know I've sort of verbalized how the others have worked, but this one doesn't make any sense when it's written down if I don't show you an example. So a whole number is divisible by 11 if and only if the sum of the digits in the places of even powers of 10 minus the sum of the digits in the places of odd powers of 10 is divisible by 11. It's harder to write than it is to do. So this warrants an example all on its own. Nothing else has, but this one does. So I'm going to make up a number. We'll see how well I do. We'll go with that. It's all right. Here's what we're going to do. I want you to underline, circle, whatever it was. I'm going to highlight every other number. Okay, 2, 5, 8, and 6 is what I chose. We're going to add them together. Okay, so 2 plus 5 plus 8 plus 6. What is that? Anybody have that one? 21. That's what I got. Okay, all the ones I didn't highlight, I'm going to add those up. I'm going to change the highlighting for them. So I've got 0, 1, 2, and 3. So if I add up 0 plus 1 plus 2 plus 3, what do I get? 6. Excellent. So we add up every other digit. That's the evens and the odds places of tens, by the way. That's describing, okay? It's every other digit. And what we're going to do is we're going to take these two digits and we're going to subtract them. So we're going to do 21 minus 6. And what is 21 minus 6? That is 15. And this number right here, if it's divisible by 11, the original number was as well. And if it's not, it's not. Does 15 divide by 11? No, it does not. So this is the notation. I'm going to write it underneath. 11 does not divide 15. 11 does not divide 15. That's how we read that. And what that means is that this number itself is also not going to be divisible by 11. Okay, now, do you have a calculator that you can check and see if this number is divisible by 11? Yes. Every single one of you does. It's called a phone in your pocket if you wanted it, right? Of course. You could check and see if this number is divisible by 11. So should you, if I ask you this question? Yeah, I would. But when you justify it for me on paper, you're not going to say, because I put it in my calculator and it didn't work. It gave me a decimal at the end. That's not what we're looking for, right? We're looking for this property. I added these numbers together and I added these numbers together, right? This is the explain part that we were talking about before from the last test. I added these numbers together, and then when I subtracted them, I got a 15. 15 does not divide by 11. You could either use symbols or you could use words. 15 does not divide by 11. So the number, what did I have? 20,518,263 will also not divide by 11. Okay, all good? Okay. The last divisibility test is divisibility test for 6. Divisibility test for 6 says the following. A whole number is divisible by 6 if and only if it is divisible by both 2 and 3. And that kind of makes sense just from the surface. 2 times 3 is 6. So it kind of makes sense that if I want to check if it's divisible by 6, I could just check for 2s and 3s. But I think it's important for me to note to you that that does not work for every pair of numbers. There are numbers for which it does work, and there are numbers for which it does not work. And we're going to come back to that idea in a moment and explore which ones does it work for and which ones does it not work for, okay? So for right now, just look at it and say, well, that makes sense, and we'll be okay. Okay. It seems like it's reasonable, right? It seems like a pretty reasonable thing to do. All right, so we're going to do an example. Our number is 24,015, and we're going to decide if it's divisible by this list of numbers. And we're going to justify it based on the properties that we just discussed. Okay, so I'm going to list them out one at a time, and we're going to either say yeses or nos, and we're going to describe why. Does 24,015 divide by 2?
No.
No, it is a no. Why?
Because it's not an even number.
Correct. I'm going to say it that way even. It does not end in an even. Okay? Notice I didn't say because it's not even. I said because it does not end in an even. It's all about what it ends in that makes that decision. How about 3? We're just going on the list. Is it divisible by 3? The answer is yes. Okay, so if you saw that the answer was yes, how did you decide?
The sum of the numbers is divisible by 3.
Yeah. So 2 plus 4 plus 0 plus 1 plus 5. What does that equal? It equals 12, right? So 3, I'll write it in words this time. 3 divides 12. So 3 divides 24,015. If in the place of the word divides, you just want to use that divide symbol, you could use that place of that divide symbol. It's a vertical bar. Okay, how about the number 4? Is it divisible by 4? No. How do we know?
The last two digits are not divisible by 4.
Yeah, so the last two digits, 15, right, is our last two-digit number. 15 does not divide. By 4. 15 does not divide by 4. Doesn't work. What's next? 5. How about 5?
Yes.
Yes. Why does it divide by 5?
The last digit is 5.
Yeah. It ends in a 5. Okay, if it ends in 5 or 0, it divides by 5. That's the rule, or the property. What do we have next? 6. Will it divide by 6? Is it a yes or a no?
No.
It is a no. RJ, how come it's a no? Do you know?
It's because it doesn't end in even. I feel like there's.
That's part of it, yeah. Yeah, no. So what's the divisibility rule for 6s? Has to be divided by 2 and 3, and RJ's exactly right. It doesn't divide by 2 because it wasn't even, right? Okay, so it won't, actually I'll say it this way. It needs to divide by 2 and 3. That's the rule, but it doesn't divide by 2. Good deal. We're at 8. It's not going to work. No. Why?
Because the last 3 digits are not divisible by
Yeah.
8.
So the last 3 digits, which is 0, 1, 5, the 0 is kind of friendly. I mean, admittedly, I gave you a nice 0 in that spot, right? Because if there's a 0 in that spot, most of the numbers we know are going to either work or not work. So 0, 1, 5 doesn't divide by 8. It doesn't work. How about 9? It's a no. It's a harder one to just look at and see. How do we decide if it's divisible by 9?
The sum of all the digits are not divisible by 9.
Yeah, we did the same as the number 3. So the sum of the digits. Notice it worked for 3, but it doesn't work for 9. That can happen. This sum was 12. And what do you know about 9? Does 9 divide 12? No. I'm going to write it this way this time. 9 does not divide 12. So 9 does not divide 24,015. Feel free to use words if you'd rather instead of using the symbols. 10. How do we decide?
Doesn't end in 0.
Yeah, this is a no. In order to divide by 10, it has to end in a 0. It doesn't end in 0. All I had to do is look the last digit. Okay, so 11's the weird one. It's not hard, it's just weird, okay? So let's actually write it out. Down here I have 2, 4, 0, 1, 5. So I've got 2, 0, 5. What's 2 plus 0 plus 5? 7. And the opposites, or the ones I haven't highlighted, the 4 and 1. 4 and 1 is 5. And then we take these two and we subtract them. What's 7 minus 5? 2. Does 11 divide 2? No, it's too small, right? I mean, it doesn't even make sense to even talk about that way. 11 does not divide 2. 0 would have been fine, by the way. Like if this had been 7 and 7, like if it said 7 minus 7 and you got 0, just like we were talking about earlier with our question before, if this had been 0, 11 would divide 0. So it can divide something smaller than itself, but only 0. So 11 does not divide 2. So 11 does not divide 24,015. Okay, what I want to do right now is push pause on the rest of this lesson, and we'll finish this lesson next time, but I want you to group up with the people you're sitting nearby, because I want to explore with you a little bit about that property for 6, because it's really interesting when it does and doesn't work, okay? So we're going to just do where you're sitting, so the 3 of you girls over here, just group up, I mean, let's literally move your desks, okay? So let's do the 2 guys right here. RJ, why don't you join them, and then we'll do the 3 of you guys. The 3 right here, so Brooke back, okay? And then, we've got evens of 3s today. Okay, these 3 right here, Okay, oh, we don't. I take that back. Okay, so Sarah and the two girls here, and then we go across here and across here. Or if you really want to do a group of 4, I'll call it good for today. Okay, so group up. Okay, I'm going to make a list. The list I'm going to make is I want to do a list that shows numbers that work with this property of 6s and numbers that don't work like the property of 6s. And your goal is to try to figure out what is in common in the list that works that fails in the list that doesn't. Okay? Common in the list that works, it fails in the list that doesn't. So I'm going to call these examples and non-examples. Good grief. Okay, so these are examples. These are ones that work. And here's what I mean by work. I'll write out the first one. So if it's divisible by 2 and 3, we know it divides by 6. Okay, if it's divisible by 2 and 5, we know it's divisible by 10. If it's divisible by 3 and 5, we know it's divisible by 15. Do you understand what I'm saying? So if I want to check if a number is divisible by 15, I can just break it down into 3 and 5 and it'll work. But there's some bigger numbers that will work too. I can check 4 and 6, not 6, 3 is what I meant to say. I can check 4 and 3 and it'll divide by 12. If it divides by 4 and 3, it will divide by 12. If I test 6 and I don't want. Do I want to do 6? We'll do 6 and 5. That's fine. 6 and 5 is 30. That'll work. Okay, let me do some non-examples. Okay, so we can't do 2 and 4 and it's divisible by 8. This doesn't work. Just because something's divisible by 2 and 4 does not mean it has to be divisible by 8. It could be, but it doesn't have to be. If we did 5 and 10, it does not be divisible by 50. It doesn't have to work that way. How about, let's try 6 and 2. 6 and 2 does not have to necessarily divide by 12. A number can be divisible by 6 and 2 and not divide by 12. 4 and 6 does not have to work for it to divide by 24. Just because it's divisible by 4 and 6 does not mean it divides by 24. Let me write one more down. 10 and, I already did 10 and something. Change that. How about, I didn't do an 8. How about 8 and 6? 8 and 6 does not have to divide by 48. Okay, so I'm going to pause right now. Your goal is to figure out what's happening on the left-hand side that makes it work and fails on the right-hand side to make those work. Okay? You do not have a lot of time. You got like 4 minutes to kind of talk and think before I spoil the fun and share what the actual answer is, okay? Talk with one another. See if you can figure out what's common and what's not.
Yeah, but then you look 5 and 2.
The numbers that go by. Oh, wait. Like, yeah, it's true.
So each of these, if you will, you get.
I spelled divisible wrong. It's all paired together. You were welcome to copy that down. I am so sorry. That's like a nightmare. Oh, but that one has students, yeah. Oh, that's right. That's what I was saying.
It has to do with the factors, not the product. Because notice 12's in both lists, right? 12's on the example side as a product, and 12's on the example side as a on the non-example side as well. It's not about the product's number, it's about the factors.
it's all by 6. It's 6 and 2 by 4. It's right by 33, but it's 6 and 4. So you're saying that on the like 4 to the left, 2, 10 to the left, 6 and 2, but then you look at 4 and 6, like right here, like these are almost right each other. This is not, this is not. These are all
These are because it just reduces to 2.
It's still divisible, right? So. The last two, right? The last two on the non-examples, though.
Maybe it's just if they can reduce each other, they can. Because I thought it was on to it.
Okay, well, so what are some of the ideas we're thinking of? A lot of people look at this and say odd and even, or odds and odds, or evens and evens, what's going on if there's an odd even property. And there kind of is, but that's not, it's because of the other property that's happening. So there is something at play in the idea of noticing the odds and evens. RJ, I heard you say something that was actually really close to. Do you remember what you said?
I'm not sure how to word it, but was on the non-examples. Like the 4 can be reduced by the 2, and let's say the 6 can be reduced by the 4. It's not, it gets into fraction territory.
Okay, so there's some reducing ability going on in the non-example list. Does everybody see that? Okay, so you're so close to having it right on. Does everybody see how on the left-hand list, the non-example list, there looks like there's something about reducing that has the ability to happen in every single example? And that's really close to the key here. Every example of the factors in the non-example list have a factor in common. 2 and 4 both divide by 2. 5 and 10 both divide by 5. 6 and 2 divide by 2. So those are the 3 that it looks like just one divides the other. When you get to 4 and 6, they don't divide each other, but they do both divide by 2. 4 and 6 divide by 2. 8 and 6 divide by 2. If the two numbers cannot divide by anything else except for 1, right? 2 and 3 don't divide by anything but 1. 2 and 5 don't divide by anything but 1. 3 and 5 don't divide by anything but 1, both at the same time, right? 4 and 3 don't divide by anything but 1 at the same time. I know 4 is divisible by another thing, but 3 isn't. 6 and 5 don't divide by anything jointly except for the number 1. That's what the kicker is.
So like if there's no greatest common factor besides
Yes,
1.
and we haven't talked about greatest common factor, which is why I'm avoiding using that language, but yes.
Okay.
If the greatest common factor of the two numbers is 1, it will work. If the greatest common factor is something else, it will not. Thank you, Ty. That was great. All right, we'll stop there for today.